everyone, we're going to get started. Today I'm very happy to introduce Goran Zuzic. He is a PhD student here at CMU, and today he's going to talk to us about the Byzantine Secretary Problem. Goran?
Thank you, Pedro. All right, so hi everyone. Today it's going to be about the Byzantine Secretary Problem. So it's a new model, very new exciting model from stochastic optimization. And let me just tell you a little bit about the name. So the secretary name is an old name from like the stochastic optimization. It's a classic model, worked for decades. Where the Byzantine is something we borrowed from distributed computing and the work of Lamport and company. All right, so this is based on a paper, joint work by Domagoj Bradac. He's an intern from Croatia. He was a summer intern during the summer, hosted by Anupam. Then the man himself, and also Sahil Anupam, former student that is now a postdoc at Princeton. All right, so let's get started. So let me give you a motivating example that's going to serve as a good mental model for the problem we're going to solve today. Good. So imagine you have one big diamond that you want to sell. So people gonna come to you and say, I'll give you $1,000 for a diamond, I'm gonna give you $2,000 for a diamond. And your objective is to sell the diamond and actually get as much money as you can in expectation, let's say. So what are the challenges in this very straightforward story? Well, the problem is that when a person comes to us, he says, okay, I want to give you this $1,000 for a diamond. You have to say immediately yes or no. Yes, I'm gonna sell it, or no, go away. And then after you actually do this, the choice cannot be revoked or changed. Like if I say to a buyer, I don't want to sell you a diamond for $1,000, I cannot call him later, oh yeah, actually I changed my mind. Or if I actually sell him, the transaction is done and I cannot really get back. I cannot get the diamond back. And also, I cannot really see into the future. So obviously, if somebody gives me $1,000 for a diamond, but I know somebody will later give me $2,000, I don't want to sell it now, I want to sell it later, but I cannot really see into the future, so what can I actually do with this? Okay, so this is a kind of good mental model to have in your mind. Let's see where it's used. Let's see some examples. So this diamond selling is also called the single item selling problem, and it's an example of a value maximization. So basically, people come with me with bids, $1,000, $2,000, and I want to maximize my value. This is like in contrast to the probability maximization that we're going to see later. But staying back to the value one, this can be generalized in multiple ways and very naturally. For instance, you might have multiple identical diamonds you want to sell. Or perhaps a little bit more intuitive, you have like ad slots on a website, you're Google, you have different ad slots, you want to sell the ad slots, and people come to you with different bids, and you want to, so be like different advertisers come to you, call your function. Do you want to give me an ad slot for 5 cents? And then you have to return yes or no, and once the function is returned, that is done. You cannot call it back, you cannot take it back, and it's done. Good. So this is like a natural example of a value maximization. So let's see what is probability maximization. Well, unlike maximizing your expected revenue, you want to maximize the probability of getting the best bid, of getting the best item, best element. So let me just give you an example to keep in your mind that's very like useful, like that will illustrate why this problem actually needs to be defined. And they're kind of intertwined in this talk, so I have to define both of them. Imagine the classical so-called marriage or the secretary problem. So the problem is you want to find your own life partner, and let's say you're going to date N people throughout your lifetime, and you want to marry the best one. So it doesn't really make too much sense to say, okay, I want to maximize my expected value of the partner. That doesn't really make sense. But what it does make sense to say, okay, I want to marry the best partner I will ever date. And I want to maximize this probability. Well, as you can see, so when I cannot really see now values, as I said, but I can see the relative ordering. So if like 5 people, I've seen 5 people, I know which one was the best out of these 5 and which I know their relative ranking up to so far. but I don't know any particular values because the value doesn't really make sense in this setting. And this problem, as you can see from the description, is a little bit harder to solve from an algorithmic standpoint. Okay, so this is like a good examples to have in our mind. So now let's see what is up next. So what I described is examples of the classical secretary model. What I'm going to do now is I'm going to formalize the model, say how it actually works out. But we're going to see a very big problem with this classical secretary model in the sense that it is going to be fragile. We'll see how. But then we want to make it more robust. So this is going to be our road, what we're going to try. We're going to try to make it robust in 1 way, 2 ways, 3 ways, fail, and then finally we're going to come at a model that makes sense. And we're going to call this model that makes sense the Byzantine Secretary model. So this is done in a paper that actually introduces the model, and so it actually makes sense to do the motions, lead you through the path of actually trying to define them and see why does the simpler models do not work. And eventually we come at something that's very robust and very, very, very surprising. Okay, then after we define a model, I'm going to tell you something about the results, and actually we're going to solve the Byzantine Secretary problem for the diamond selling. So value maximization, diamond selling, we're going to tell you how to do it in this Byzantine Secretary model.
Diamonds have anything to do with secretaries?
Sorry?
Do diamonds have anything to do with secretaries?
Not really.
Secretaries?
So
What,
I thought you get it.
you are right, but this is the problem, this is the model.
Oh, okay. Oh, I see.
That's right. So this, exactly, you're right. Okay, so, and then we're gonna state some open questions. Good. So let's define our formal classical secretary model that's been studied for like decades now. Okay, so we have our time horizon that's between 0 and 1. That's when your bits come to you, that's when you say yes or no to them. The values are worst case. So we don't assume anything about the values, whatever they are, we cannot say anything. But our simplifying assumption is that the arrival times are uniformly random. So basically a bit comes at a uniformly random time from 0 to 1, and that's going to be our simplifying assumption. So let's see an example how it actually works. At time, let's say 0.1, I get a bid at this of this value. Do I take it or not? Let's say no, I don't take it. Then I get another bid. Sometimes, oh, this is pretty good, but it's kind of early, so I don't want to take it. So I say no again. Do I want to take this one? No. Do I want to take this one? Let's say no, 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 no. And I say, oh, this is a really high one, and it's getting pretty late, so I better take something, and then I take it. And after, whatever happens cannot influence me at all. Like I cannot pick anything later because I had a single item, a single diamond, I sold it to this guy, and that's about it. And in the probability maximization case, I hope this is the best one. In the value maximization case, I hope this is comparable to the best one, not too much lower. That's what's going to be the good part. Okay, so this is going to be how it more or less works, if you imagine this came at random times. And now let's talk about one classic algorithm for this problem. It's called the Incans Algorithm. And it says that you can actually achieve a pretty good, a constant approximation. So with constant probability, you can get the highest value bid. In particular, this constant is 1/4, and we're going to improve it a little bit later. So the algorithm is very, very simple. And it says the following. Take your time horizon, split it into 2 halves, the first half and the second half. Ignore everything or just observe everything in the first half and then reject it immediately upon observing. And then in the second half, when an item arrives, if it's better than everything you've seen so far, that's when you actually accept it. That's the entire algorithm, right? Pretty simple. Now, let's see, why does this give you 1/4 probability of picking the best element? Well, let's say it's pretty simple. So I say, let's condition on 2 events. The first event, that the second maximum bid comes in the first half. This happens with probability 1/2. And then condition that the actual maximum comes in the second half. This also happens with probability 1/2, and these two are independent, so it's 1/4. Now, if this happens, I guarantee to you that you're actually going to pick the maximum element. Why? Because you're going to observe the first half, and then we're going to set our threshold as the second max. So we're never going to accept anything below the second max, and we're going to accept anything above it. And the only thing that's actually going to trigger our threshold is the first max, and we're going to get it. That's the only case, and we're always going to get it, condition on these two events, and we get a 1/4. Should be fairly simple.
So obviously they're,
Sorry?
obviously they're not perfectly independent, right? Like if there's only two, for example, then they're disjoint events.
Sorry, if there was only two,
There's
then
only two items, for example, the events at or they're perfectly correlated, rather, right? If the first max occurs in the second half, and the second max always occurs in the first half.
not really.
He's doing random
Yeah.
roll time, right?
So I don't
I
have.
see, it's not the order. You're saying just half the time. I see.
Yes, that's a very good question, but
Yeah.
this is actually uniform time from 0 to 1, and it's actually uniformly random between 0 to 1. Perfect.
Okay.
That's a good question to clarify. Thank you. Now, okay, this is like the Dynkin's algorithm. I urge you can remember it. So split it in two parts. Observe the first, pick the maximum in the second, whenever you see one. Now, so this gives you 1/4, and this can be proved to 1 over e, which is 0.37. This is actually the result done by Dynkin in 1963, so pretty old. And the 1 over e is the optimal value. This cannot be improved. And okay, so this is like a very simple model. You can generalize in different ways. As we mentioned, you can take multiple items. You can even choose matrix independent items, whatever are matrix, doesn't really matter. But you can generalize in various ways. But
What I want to know is, what happens when you lose, when you don't get the best? What if you just got second best? That wouldn't be so bad.
exactly,
Or the
that's
third best.
you are.
So it seems like you're more interested in that kind of question.
Yes,
At least as interested.
You can do that, and then you would be usually assigned their value. So you have to say what's their values, right? Then you just do the value maximization problem, right?
The diamond one.
Yeah, exactly. But in the probability, so the thing about here, the Dynkin secretary solves the probability maximization problem. It's actually the best case scenario, the harder problem. But if you actually want to do this, that makes absolute sense, but then you need to give the scale. You need to like somehow define the values, and then there are multiple ways to do it, and then you're just talking about regular value maximization. In worst case, the approximation factors are the same. You cannot get better than 1 over e in either the probability maximization or the value maximization case. Like you can always say that the best person is so much better than the second best person, that getting the second best person is not really interesting. Now, what you're suggesting is setting some kind of a linear scale, and that's an interesting question in itself. I've never seen any work done, but that's an interesting question. The only problem is like you have to make this somewhat arbitrary choice of a scale. How do their values correlate to each other? Good. Okay, so there's a simple model can be, oh, Gary.
Quick question. So let's see, so all the bids have to arrive within the first unit of time?
Yes, so there is
All the
only
bids
all the bits.
All the bids?
Yes.
And then they come in a random time, right?
Uniformly random time, yes.
Uniformly random.
Absolutely. You're right. Good. So this model is like simple.
You don't get to know n, though, the total number of bids until the end.
You actually, so
Actually, you could do that, because by the time the half is around, you got a good estimate of.
yes,
total number of bids.
you can estimate it, but otherwise you also you can kind of guess it. It only loses you a small log n factor if you actually don't know. But for now, let's assume that you know it. It's a simple rule if you know it, and if you don't know it, well, you can guess it up to a factor of 2, and everything stays the same. In this talk, we are not worried about constants too much.
If you knew it exactly, then you could solve Danny's problem, and then you would, if you didn't find a big one, then you would just pick the last bid.
Sure, but that last bit is probably bad, and you're going to get a value of 0.
If Danny's had it, may be better than having no diamond.
True, but for purposes of this, it's a 0. You're absolutely right, but for this purposes, it's a 0. But you're right. So for now, just to have a point, assume you know n. So your own is going to pick the last one, but it's generally not going to help you much. Like only a 1 over n factor or something like this. Good. Okay, this is a simple model. However, it has a problem of being fragile. In what sense? So we have this very strong assumption that every one of those elements, items, are well behaved. So each one of them is like uniformly random. So what happens if there is like one outlier that's like maliciously injected, or like somehow happens to be some random big outlier in position number 1? It messes up your Dynkin secretary algorithm completely. Because what happens if you have your outlier, a big outlier in the first half, you're gonna observe it, you're gonna set your threshold as this at this outlier, and then you're gonna never accept anything afterwards, so you get a 0. And you can imagine some malicious actor. If you're Google, somebody writes a script, puts it at like ×0, and you're dead in the water. It's not that you can do much, so we want something a little bit more robust than this. And now we're gonna try and formalize this. What is our robust model? We have a couple of trials. And then we're actually gonna find the right model and then talk about the results. So the first trial, I'm gonna just say a little bit. The first trial, we're gonna say, what if the arrival times are fully adversarial? This is gonna be a fail, too hard. You cannot never do anything here. Then we're gonna try, let's say, a mixed. Sometimes some of them are adversarial and some of them are random, well behaved. It's also gonna be too hard. And then we're gonna do a few more tweaks, and eventually we're gonna arrive to our proper Byzantine secretary model.
So is this a standard adversarial model where the adversary knows your algorithm but not the probabilities?
Yes, exactly. That is right. But there is just a couple of steps in between to formalize this completely. So we'll say this. The adversary first chooses the bit values, or the relative orderings, and then the bits get shuffled randomly in the interval. Yeah, sure. So first you give the algorithm, then the adversary chooses the bit values, then the bits get shuffled randomly, yes. So first you give the algorithm, but not the, exactly. Good. Algorithms, bit values, random shuffling. Perfect. So this is actually a project where it actually makes sense to know the exact order of things happening. Good. So let's start, and then a few more tweaks. So let's start. Fully adversarial arrival times. So basically, in this hypothetical model, the adversary chooses both the values of the bits and when do they arrive. And you want to get the best bid. Completely impossible. Like in the sense that you can only do 1/n. You can get the best element with probability 1/n, which is kind of trivial because that's what random guessing gets you. And the same thing holds for like if you're in probability maximization or in value maximization world. It's going to be mostly the same factor up to like something later in the talk. So let's see an example. Let's actually prove this well. It's pretty simple. Let's say I start, my first bid is this. Do you want to take it? Well, let's say it's too early. I do not want to take it. Let's say another bid comes. Do you want to take this bid? Sure. Anyone? Sure? Let's say no. Sure. Well, then this continues on. Sorry? This one? This continues on, and you have to guess when will it stop, when will it drop. So what I'm going to do, the adversary going to present you increasing and increasing bids, and eventually they're going to drop. You need to guess at what point do they drop. And maybe you want to continue on, but actually this is the decreasing point, and you have to guess this. There is no way for you to tell. Exactly. That's right. Now, good. So the only thing you can do is guess where is the point of drop, and this is 1/n, and that's the best you can do. This proves the lower bound, and that's it. You cannot do anything. So this model is too hard. Let's try the next model. Now, we don't have all of them that are adversarial. Now we're going to divide the elements into two groups. The green elements that are well behaved and come in a random order, and the red elements that are badly behaved and are maliciously injected by the adversary. So we'll say that G is the number of green elements and R is the number of red elements. The values are still adversarial. What can we do here? Well, as I spoiled the result for you before, we cannot actually do much, and we can get only a 1 over r approximation, r being the number of red elements, and the example looks kind of the same. So you want to get the highest red elements. I'm going to present you an increasing sequence of red elements followed by a drop. You have to guess where the drop is, and the green elements are somewhere at value 0, and we don't really care. They can, they don't really help much. Even if I told you up front what's a green, what's a red, you cannot do anything. So
I don't understand what the green and red elements are.
oh, sure. So red elements, adversarial arrival times. Green elements, uniformly random arrival times. Does it make sense?
The values for both are adversarial? Or?
Yes. So let's define the ordering one more time. It's actually helpful, and I'm even going to write it down. So this is the ordering of stuff that happens. You present the algorithm. Then the adversary chooses values. Then nature comes. Random shuffle. Oh, uses values and red times. And then nature comes and randomly shuffles green elements.
The adversary knows which ones are going to become green.
Yes.
So fixed red times and green times, and
He
the green ones are perfect.
Exactly. So he says, okay, this is the value in the green elements, this is the value of the red elements, he pushes the red elements, and then nature comes and shuffles the green elements.
There's no advantage of whether you pick red or green.
Sorry?
So you could imagine that the adversary wants you to pick one of their red elements and not a green one. Or vice versa, that there would be some win, because you could imagine the red ones are him, and the green ones are some other people, right?
Well,
I mean, more natural would be that he only wins if you pick a red.
so actually the thing is, so imagine you're in the, that's a good question. So imagine you're in like this Google model. So each one of these people gives you a credit card. And if somebody says, well, I'm going to pay you $1,000, you can actually charge the credit card for $1,000. So I'm actually happy choosing the red one if the value is pretty high.
You mean you as a picker or you as a seller?
Me as a Google, me as the seller, the one that picks. Sorry, the one that actually picks the one. If like this element gave me his credit card and he says, well, I'm going to give you $1,000, and I'm actually, I'm going to charge the $1,000 if that's what I pick. So I'm actually happy picking a red one if that's going to be my the best value possible. Does it make sense?
Yeah, but the other model would be that there's a bunch of people get together, and I say I'm a red person, and us red people get together. We say we want to buy this diamond on the cheap, and so what we're going to do is figure out how to get it on the cheap. And if a green person buys it, that doesn't do me much good because then I didn't get the cheap diamond.
I mean, but you're asking from the adversary's perspective. I'm the one selling the diamond. I want to optimize for the sell, right?
Yeah, but you can also imagine that the buyer wants to optimize their position. There was some advantage. Why would a red person do this?
Actually, can you repeat one more time?
Well, don't worry about it. But it seemed to me that the obvious thing would be that the red ones are bad agents and they're trying to optimize their position.
No, I mean, say for example, the red is the auction house, right? They want you to sell to someone else for a high price.
Okay.
Red
So
is
they
the
just need a
auction
person.
house. No, I thought, the reds are, malicious bidders. They want to lower your price, actually.
Right.
They want you to not sell the diamond.
Right, but
It's the other way around, right? So the red ones want you to, let's say, not sell the diamond or get a very low value.
So,
Yes,
to
Isaac.
be clear, this is an adversary for your algorithm, not an adversary for like this theoretical buyer. The adversary is trying to make your algorithm fail.
Yes.
So the algorithm does something that's not what's optimal.
Yes,
Algorithm-
exactly.
The adversary is trying to make there be something that's optimal, and you not do.
Yeah, if I'm Google and want to maximize my profits, the adversary wants to minimize them.
I think the point is that this is an adversary that's not self-interested, they're sadistic, right? They're merely trying to hurt you, not help themselves. Okay.
Okay, good. Yeah, good. Perfect. So yeah, we have this objective. We wanna protect against any kind of adversary. Yes, Alice?
Just to be clear, when you say that nature randomly shuffles the green elements, nature, it's not taking a random permutation. It's still doing a uniform zero.
Yes.
for all the green.
When I say shuffle, I meant like samples a uniform random number from 0 to 1 for every green element.
Okay.
Roy, here you have a?
Do you have an upper bound for this, or like what can you?
So this is an impossibility result.
Sorry, I mean the other way. Like what
So possibility result. That's
You should be looking to pick a random one over
Pick a
R.
random red element.
sure, but that's 1 over n.
A random red element.
Oh, you don't know is it red? You don't know is it red or not? Good question.
I think you can make it 1 over R plus 1. If you first place the green one and then the adversary, like, there's only one green one basically,
Okay.
and then the adversary basically like makes the same picture.
Oh yeah, you can definitely make it 1 over r plus 1. Absolutely. 1 over r, I didn't think too much because 1 over r, sure, it's pretty bad. I can give you, so what would be a bad example when there is only like one red, oh sure, so let's do this. Actually, imagine there is a bunch of green elements and only one red element. And now the question is, can I get a constant approximation or get 1 over n? So now it's, okay, I actually thought about it. So if the red element is the highest, if the red element is not the highest, is not even in the, let's say, the top 2, then you can just do the secretary. You just do the standard Incans algorithm. Now, if the red element is the highest, now you gotta recognize this highest maliciously inserted value in a bunch of randomly placed stuff. And that's a good question. I think the optimal that we came up with is 1 over log n. And basically you're gonna choose every local maximum that you see. Every element that's like biggest than everybody so far, you're gonna choose with equal probability. And in expectation, you're gonna be like log n of those. So that's what you do then.
How do you know how many they're going to be?
Oh, because they're randomly shuffled. I'm saying this like one red element and a bunch of green elements. Then you know because it's, you know, this green element plus the expectation for the green stuff plus 1. And this is the most extreme example where you see the
So you see
dichotomy.
you see a local max.
Yes.
How do you know with what probability you're choosing it or not?
1 over log n.
Okay.
Sure, right? Times constant, which we don't really care. Good. Okay, so if we green and red elements want to choose the best red one, impossible. 1 over r, that's way too bad. We want like constant or something close to it. Let's go further. Now, what did we see? These are my good actors, and these are my malicious actors. Something similar to what Gary suggested, like maybe I don't really care, like malicious actors didn't really want to give me anything. Maybe I just want to compare myself to the green actors, to the good actors, and that's going to be my question. So I have green elements, I have red elements, but I'm happy if I get the best green element or better. Third model, almost there. However, this also really doesn't work, but it's very close by, so you also get a 1 over r. Actually, 1 over r plus 1 as Roy mentioned, but you'll see. Basically, how does the example look like? So what do we say? So we're happy to get the highest green element or better. So even if you choose a red element that's above the highest green, we're happy. So let's prove this lower bound again. It's pretty simple. This impossibility result. We get this element. Do we take it or not? Let's say no. And then, well, actually, it was a red element. Let's see this element. Well, actually, it was a red. What about this element? Well, actually, it was a red. What about this element? Well, actually, it was a red. What about this one? Well, that was actually the optimal, but you have to guess where it was. You have to guess the jump. And the way how you actually construct this example, you make one big green element. Everything else is around 0. And then you make an increasing sequence of randomly placed red elements, but are increasing. That's how you construct this example. You only get 1 over r plus 1. You have to guess the position of the green element.
But you're allowed to pick red, right? So you may pick that last red element.
Sure, but this is your threshold and this is below it.
By what?
Oh, sorry, maybe it's not clear from the picture, but this is...
Centrally to central.
You're right, but yeah, it's a little bit It's a little bit too low, the last red element, yeah. So this is an example that will show you that actually you have to guess the position. You have to guess the jump. Okay. So this is also a little bit too hard. So now let's do the actual thing that works. Now this might seem like kind of out of ideas. But what I'm going to do is, okay, maybe the first green maximum didn't work. Let's choose the second green maximum and hope that works. But surprisingly, that's actually something that's going to be pretty effective. So, and that's actually going to be my Byzantine Secretary model. So let's remind ourselves, we have green elements, uniformly random arrival times, red elements, adversarial bids and arrival times, and our benchmark, benchmark, is set at the second green max, so the second highest green element, the second highest green element, or anything better than it. That's going to be my benchmark. It makes sense in the probability maximization case. What is the probability that my pick element is at least as big as the second green max? It also makes sense in the value maximization case. What is the ratio between the expectation of my algorithm and the second green max? Perfect. So why did we do this? As we're going to see soon, the results are actually surprisingly robust and strong. And it's not really the first time in history that people care about the second max. Like victory auctions, for those who didn't know, actually are defined with respect to the second max. Good. So what are the results that we have in this model? This somewhat strange model, but still it's the simplest model that has no stupid counterexamples, no stupid impossibility results. Well, I claim for this diamond selling problem, so you have a diamond, you want to sell it, maximize the expectation with respect to the second green max. You can be 1 over log star n squared competitive. Like, okay. So is it a constant? It's not a constant. It's a little bit worse than a constant. But it's kind of the next best thing. So that's pretty amazing. Now, in the probability maximization case, which is a harder problem, you don't even get this. You get something a little bit worse. You get a 1 over log n squared. But still, it's amazing because everything we had so far was 1 over r. Or stuff like that. And note, as I mentioned, so before we had impossibility results of 1 over r. Now this has no dependency on r. So what does this mean? Even if your entire input is composed of all the bad elements, all the malicious elements, red elements, and only 2 of them are good, are well behaved, you still get this approximation. You still get these competitive factors, which is very, very robust, very surprising actually. Good. Actually, yeah, somewhat
So in that case,
very
R
strange.
then, right?
Yes, but the dependency, this is like no dependency. But the point is, if your entire input is malicious, intuitively you would say, I cannot do anything. But actually you can. So let's see what we're going to do. Oh, Nama, sorry.
Aren't you actually not doing anything? If the entire input is malicious, there is no second green element. Right? So you're allowed to choose anything?
Not really. So you still don't know. Maybe the red elements have values below the green elements. Maybe there are some in between, some below. Maybe they're all above.
There's always going to be 2 green elements?
Yes, there. Oh yeah, I'm
so
sorry.
you guarantee that there are 2 green elements?
I'm sorry. Yes, if there are no 2 green elements, then I say the benchmark is 0. So it works, but because of a trivial reason. You're absolutely right. Thank you, Nama. Yeah. So if the entire input is malicious except for 2 green elements, you're still good. You can still do this. Good. Now, what we're going to do, I'm going to explain you this diamond selling result, as I said. So the value maximization single item. And unfortunately, since this is a speaking skills talk, I cannot really go into the probability maximization. But that's where all the fun happens. Like, let me just give you one reason. So we actually have an algorithm for this, and it's pretty simple. I will explain it in full detail. However, for the probability maximization, we have no idea how the algorithm looks like. We have a very non-constructive way of describing it. Which is a strange thing, you know, an algorithm but not constructive, like, well, what's happening here? It's about, we use like the minimax principle, like duality, however you want to call it. But yeah, that's where the fun is, but this is going to be a nice to illustrate like a big portion of important ideas. And it's a really good as an introduction, and that's like, after this, you know, you can talk to me and I'll explain everything what you want to know. Good. So let's go into the diamond selling, the value maximization single item case. So what I'm going to do, we get so as a reminder, we get a 1 over log star to the C, some power Pauling log star competitive ratio. And the way I'm going to make this work, I'm going to explain you a couple of ideas, a couple of tools. And once I explain those tools, we're going to try to use them together and arrive at some good algorithms that are going to have some good competitive ratios. Good, so the tool number one, and the simplest of them all, is random guessing. So imagine there is one element that's extremely big, n times bigger than the benchmark. Then just by randomly guessing which element there is, I'm going to get my benchmarking expectation. Why? Because the probability that I pick this one element is 1 over n, and then if I pick it, I get n times bigger than the benchmark, and in expectation, it's exactly the benchmark. Perfect. So yeah, tool number one, random guessing. Very simple. Let's go to another simple tool, the bucketing method. Now, let's say that I know that the benchmark lies between some interval, so some a and m times a. So some interval.
What the benchmark is again?
The second maximum, the second green maximum. Like imagine any element you want to get.
Yeah.
So in this case, it actually does not matter. So imagine, for this case, imagine there is a sequence, or there is this random allotams. One of the elements has a value of opt. You want to get opt or better. Right? Makes sense? In particular, the benchmark is the second green maximum. But for this result, we don't really need that yet. We're going to use that a little bit later. This can be the red element. You can set now the benchmark whatever you want. The biggest red element. But yeah, imagine there is one element with value opt. And we know that this value opt falls between the range a and m times a, so a multiplicative m factor. I can get a 1 over log m competitive ratio by using bucketing. How do I do it? I just
Wait, what is m again?
Some number, some scale. It's my scale, multiplicative scale at which I know where my benchmark lies in.
So you have upper lower values.
Exactly. So it doesn't matter where it starts or it ends, but it matters that it's a scale of m size. So pick any m you want. It works for all m, right? That's the thing what I want to do. It's a free argument. Good. Okay, so how do we do this? We do partitioning. You partition the values of the elements into log m buckets. So you go from a to 2a, from 2a to 4a, to 4a to 8a, and so on. You geometrically increase them. You have log m buckets.
Is that a typo? It should say 2a to 4a. The second element of that sequence.
Oh, absolutely. It should be 2a to 4a. You are right. You're right. Good.
That's what you said.
Yeah, 2a to 4a. That's right. And then you end at m over 2 to m times a. Good. You partition them. Then you have this log m buckets. You choose a random one. Uniformly random one. And hopefully you chose the correct bucket. It happens with probability 1 over log m. And then if you chose the correct bucket, you choose the first element in the bucket, and you lose another factor of 2 because the buckets are of multiplicative scale 2, and you get your expectation of your algorithm is the probability to choose the correct bucket times the value in the bucket if you choose the correct thing, so opt over 2, and which is 1 over log m approximation. 1 over log n times the benchmark. Perfect. So bucketing, pretty simple. I think we're ready to go on. So the thing to remember, if we know the opt falls in a range of size m, we can get log m. That's what the thing to remember. Next things up. The third, we're going to use the third tool. We're going to use the classic Dynkin Secretary algorithm. Now, let me just define one definition. Let's say an element is a big red element, if it's red, and bigger than the second green max, bigger than the benchmark. Simple definition, right? So when does the element become a big red element? In terms of this like step, what happens when? Well, it happens here. Big reds are defined, and also their positions. So once the adversary chooses the values and the placements of them, we know where the big elements are, and then nature shuffles the green elements around. The big position of big red elements does not depend on the positioning of the green elements. Okay. So now, the claim is the following. Consider a time interval between A and B. And suppose there is no big red elements there. Then, you can get, by running the Dynkin Secretary algorithm in this interval only, ignoring everything else, you get the size of that interval squared times opt. Why?
They both land there, then you're good.
Sorry? Yeah.
If the second and first land there, then you're golden.
Exactly. A little bit more. If the second land in the first half of it, like b minus a over 2.
Get 1 over e is what I'm saying, if they both land there.
True. Yeah, fine. Absolutely. Yeah. That's, David is exactly right. Exactly. If they both land in the interval, you can just run the standard Dynkin Secretary. You get exactly the same thing as before, except b minus a squared factor. So that works. So basically, what do we know from here? If there is some interval without a big red element, we can get a good. If there is a big interval without a big red element, we can get a good ratio. So essentially, every big interval we have a big red element. That's the takeaway from this tool. So let's combine these three tools that we use and arrive at a log n algorithm as a warm-up. 1 over log n competitive ratio algorithm. All right, so this is what we're going to do. You have your interval, partition it into 2 halves, 1 half, second half. And now we're going to have a bunch of algorithms. We're going to choose randomly from each one of these algorithms. You're going to choose randomly from them. So with 1% probability, pick a random element. So this 1% is a constant. We don't really care. You just choose something small enough that you can run everything. When you do this, you are done unless all the elements are within n times the benchmark. So if there is any extremely big element, you will be done. Otherwise, you can, from this point on, you can assume this holds. Or we're done. So that's good. We even get a constant approximation if you're done. So we're really good. Okay, so algorithm number 2. You run the Dynkin's algorithm in the first half. So now, as we said before, either we get a constant approximation if there is no big red elements in the first half, or there exists a big red element in the first half. 1% is a constant, we don't really care. Okay, so now we know there is no extreme elements, and the first half has a big red element. Similarly for the second half. Now the second half has a big red element. And finally, you do the following. You observe the first half and assign A to be the maximum thing that you observed. But now you know that in the second half, everything falls between A, the benchmark falls between A and A over N, because we know that A is at least the opt because there is a big red element in the first half. But you also know it's not N times bigger than the opt, because otherwise you would be killing this condition. And now you just run the bucketing algorithm. So we know everything fits within a multiplicative factor of N. You use bucketing on the second half, and you get 1 over log N. Pretty simple. Good. So now we're almost done, but now we use now maybe the hardest or the most coarse tool of all, but it's pretty simple. And I call this tool the done or refine strategy. Actually, the name is from Sahel. Okay, so what's the setting? Imagine you have two intervals, one next to each other, somewhere in the middle of the time horizon. And you know that in the first one, there is the benchmark is within a factor of m. You know it's between a and n, a times m. Then you can there are three cases you need to consider. The small case, in which there is no big red elements in the first half, in the first interval. Then you just run the Dynkin Secretary, you get the size of the first interval polynomial in that. Good. Now, the large case we have where there exists a value bigger than log m in the first interval, times opt in the first interval. Now, in this case, you run the bucketing algorithm. So you divide into buckets, you pick the right bucket. There is log m of them. And in expectation, you're going to get your opt times a constant. Okay. So in those two cases, you are done. However, if you are not done, so these are good cases. If you are not done and you don't get a constant times opt, then you refine. Now we have the last case, the medium case, where there exists a big red element in the first interval, but it's between opt and log n times opt. But then what do? I observe the first interval, I observe the maximum, and I know this maximum is now a log m approximation to my benchmark. So basically, what you should remember, I can go from an m scale to a log m scale by having two consecutive intervals that are not too small. Good. So that's the last two, done or refine. And with this, actually, we can get a log star pretty easily. So what do? We partition the time horizon into t log star n many intervals. And then we randomly choose between a bunch of algorithms. Choose a random element. So that is done unless there is no extreme. That's done if there is an extremely big element. Otherwise, everything is within a factor of n. Otherwise, we pick a random interval and run the Incans Algorithm in. So this ensures that every interval has a big red element. Otherwise, we get poly in 1 over t approximation. So 1 over log star to the some power. Okay, so now we know there is no extreme elements, and every interval has a big red element. Then we do the done and refine strategy in each one of them. In the first thing, we know there is a factor of n. So in the first interval, we know that the benchmark falls within a factor of n. Then in the second, we know that the benchmark falls within a factor of log n. And then it goes to log n, log n, and so on. After log star many steps, you get a constant. That's how the log star is defined. So after I do done and refine for log star many steps, I get a constant approximation to the opt. And then I can get a constant approximation very easily via bucketing or thresholding or whatever you want. Good. So that's it. That's 1 over log star to the C algorithm. If you optimize for this constant C, you can get a 2. We won't get into that. But this gets you a polynomial in 1 over the log star n. And that's it. So now we proved exactly as I said. For the value maximization case, the expectation case, we proved 1 over log star to the C. You can get it to 2. But the open problem, we actually have no lower bound. We actually don't know should this be a constant. We think it should, but it gets pretty complicated.
Why do you call it super constant?
Like more than 1 over, like, is there an impossibility result that says, well,
No constant.
that's like not a constant, like bigger than like smaller than a constant, like little of 1. Can we prove that you get little of 1 competitive ratio?
Subconstant upper bound.
Oh, I'm sorry. Actually, you're right. So what I wanted to say, I usually write the results in the form of 1 over the competitive ratio, and I want to say, is it true that the competitive ratio should be a super constant? That's what I wanted to say, yes. So we do not know. Maybe this should be an O of 1. So that's a big open question. For also the probability maximization and the value maximization case. And then, as I said, the probability maximization is all constructive. Can we make a simple algorithm such as this one for it? It'll be great. Then some other result that we actually have in the paper. So they're going to work it themselves up. But we can get like a constant approximation for when you choose multiple items, when you choose many items, log n in particular. This was done in the paper that this talk is based upon. Then another question that we can ask is, can we get a 1 minus epsilon competitive result? Well, we can. This was done like a couple of weeks ago. Not particularly optimized for how many elements you need to choose, but what can you do? Maybe you want to optimize for this number, which I didn't even state. But this like leads you to the actual open questions. Is what if you have some kind of a more general constraint? What if you have a knapsack constraint? So basically every item has some value, they're not 0 and 1, and you want to fill up your knapsack up to some value. Can you actually optimize for that? Or even more generally, can you do LP constraints? So these actually settings have been studied in the secretary model, and you can get very, very good results. Like in the LP setting, I believe, if the values are much bigger than if the budget is much bigger than the values, then you can get like a constant approximation in the secretary model, where you have to like choose columns as they arrive, which is like amazing. And the question is, can we generalize it to the Byzantine secretary model? All the work done in the secretary, what can be generalized and what cannot. And that's about it. Thank you. Yeah, David.
Can you interpolate between the non-red elements and arbitrarily many red elements scenario?
Oh, like something that has some kind of
Dependence on R, basically.
Dependence on R?
Right? So if R equals 0, you're in the classic secretary
yes.
you can get a constant.
Good.
Now you're saying if R is at least 1, you can get 1 over order log star squared. Right?
Good. Good question. So I don't think that's a particularly interesting question because the dependence is very weak. Dependence is so weak. So I actually believe that the result is constant, at least in the, let's say, no, I don't believe that. No, I believe that the result is super constant, but it's super weak dependence on n. So in particular, its dependence on R is even weaker. So that's why I am not particular.
If R is 5, I don't know, R is log n.
Yeah.
All your bound says you can get 1 over poly
yes.
log star n, right?
That's true. Okay, fine. So maybe in that case it would be interesting. I'll tell you the following. If R is constant, you can easily get a constant approximation. You sample everything with probability 1 over R. With constant probability, no red element remains. and with constant probability both the first and the second max remain, and then you're around Dynkin secretary. So that's easy, yes. There is some kind of a polynomial 1 over R dependence. And then you take the max. So that's very interesting case being solved. Now you want to say what's the actual dependence on R, and that is interesting, but not too much because I feel the dependence is very weak.
I mean, you're not quantifying it, you don't have a dependence on R so far, right?
Yeah, but it's a
1 over poly R.
Well, sure, but it depends on n. It's so weak that I don't think it matters too much what's the actual dependence.
R is log star, right? Let's say R is log star.
Yeah, sure.
Log star is...
Even a concept, like, I guess like a related question, is like, if you start with the secretary algorithm, you're saying something very reasonable, which is that if I know you're running secretary,
yeah.
Here's what I'll do with one bad insertion. I'm going to insert something like that's super valuable at the beginning.
Yes.
I have that power. And now you'll never pick anything good. So now you can ask, if I know you're going to insert like one thing, and you're going to insert whatever you want, and it's going to be however large you want, what's the best algorithm you can create?
Good. So,
like, you know, qualitatively, how far down does the 1 over E go?
That's a good question. Yeah, that is an interesting question, and the answer is I do not know. So constant, obvious, by subsampling.
Sure, but like, it's different if it's like, you know,
absolutely.
2E, and if it's 1 over E minus something tiny, or if it's 0.0001.
Yeah, that's actually a good direction to search for. We did not search in that direction, but you're absolutely right. I don't know. We didn't look at that much. We didn't look at that, but that's right. Yes, Danny?
So, what is hiding in the O, and why do you leave an O there?
Some pretty big constants. Like, so let's say, well, it became kind of too complicated to work. I mean, we were too lazy to work them. We were kind of too lazy to work them out. We know it's a constant. I would guess actually for this one it shouldn't be too big. I would say up to 10, maybe 20 maximum, because
they kind of swamp the log star.
yeah, usually. Yeah, you're actually right. For any kind of a theoretical, for any kind of a practical thing, it's probably much bigger than a log star.
Yeah.
But yeah, we would actually want to know, can you do a constant? That's actually what we would be very interested in knowing the result for. But you're right.
More questions?
Ainesh? We thought about it. We don't see why the third max helps at all. I don't believe that. I cannot see an argument that would work with the third max and does not work with the second max.
So do you know what K max you need to look at to get a constant for?
That's a good question. Well, if you make for very large values, then it's easy. Yeah, I don't know. I don't think. I don't see a way how would a log star work. I don't see how anything smaller than a polynomial in n would help you. And that's a very non-interesting value. I don't know. We didn't think too much about it. The third, I don't think the third helps. Now, a log n could help, but we don't see how. That's an interesting thing. Good.
Running out of time, so let's just think Goran, take all the questions offline.
Thank you.